As we start our unit on triangle trig applications, we are now going to branch out beyond our special triangles and things we can do without a calculator, and we're going to be using our calculators a lot. And I want to review some problems, the SOHCAHTOA type problems that you have, similar to what you maybe did in geometry. In these triangles, we are given right triangles and we are solving for a missing side or angle of a right triangle. So the goal is to look at the triangle, so look at the one on the left, and see how these two sides are related to this angle. For this angle, 6.9 is the adjacent side and 8.6 is the hypotenuse. Since we have an adjacent and a hypotenuse, we're going to use cosine. So we can say cosine of the angle, and this symbol is an alpha, Greek letter alpha. Cosine of alpha is 6.9 over 8.6. So in order to solve for the angle, I'm going to have to use inverse cosine, because inverse cosine of a trig value gives me an angle. So inverse cosine of 6.9 over 8.6 then gives me my angle theta. And I can check on the calculator. I wanted to show you a couple things. If I do this 6.9 over 8.6, if I'm in degrees, and you can see if I hover up here I'm in degrees, I get 36.6472 degrees. I also changed my calculator into radians to show what happens. If you happen to be in radians instead of degrees, it'll say RAD here. You'll get an angle in radians. So don't let that throw you if that happens. Just change it back to degrees and get the angle in degrees. Sometimes later we will be doing applications with angles and radians. So my correct answer is 36.6 degrees. Make sure to give me at least one decimal place when you're doing angles in degrees. Okay, the next one. Now I'm solving for a missing side, and if you look at the 3.5 and the x, they are the opposite and the adjacent side to angle 29, so I'm going to be using tangent. So I say tangent of 29 is equal to 3.5 over x. Now for some reason solving this little simple expression seems to give people a lot of trouble. If your x is in the denominator, multiply both sides by x to start out with so that you get the x out of the denominator. So I have x tangent of 29 is equal to 3.5. Then I can divide both sides by tangent of 29, and I have x equals 3.5 divided by tangent of 29. And we can check on the calculator. I've already got this one done too. So 3.5 divided by tangent of 29 is 6.3. And this is centimeters. So x is equal to 6.3 centimeters. How many decimal places should I use? Kind of look at the problem. If there was one decimal place in the side on the problem, then in the given information, then that would be sufficient for the answer. For angles, and I want you to give me that extra decimal place to make sure that it is the correct answer and not just something that you maybe estimated or did something incorrectly and happened to get close or something. This third one, we're doing an angle again, and notice for this angle the opposite side is 23 and the hypotenuse is 45, so we're using sine. So saying sine of theta is equal to 23 over 45. Once again, since we're trying to find the angle, we have to take inverse sine of the trig value, 23 over 45, in order to get the angle. That should say theta equals. And I did that on my calculator already, and I got the answer 30.7. I want to show you a nifty little trick. If I do inverse sine of 23 divided by 45 and push enter, it gives me inverse sine of 23 over 45. But if I add a decimal point, see the little decimal point? If you put a decimal point in there, it will give you 30.7 without having to do control enter. Just a little tip. So the answer here is 30.7 degrees. The next section I want to look at is talking about angles of elevation and angles of depression. For your viewing pleasure, I have, I'm going to move this over here for right now, I have drawn a vulture looking hungrily down at a rabbit. The rabbit is not dead yet, but he's dying. So here's my vulture looking down at the dying rabbit. Now, the angle of elevation and the angle of depression are always measured from the horizontal. So in this case, I'm going to be looking at how far down the vulture is looking. So if the vulture was just looking out in a horizontal direction, so this would be a horizontal line of sight. This vulture is now looking downward, so this angle has depressed or gone down. So this is an angle of depression. Actually, the only person depressed in this situation is probably the poor rabbit who is about to be eaten as soon as he dies. Although I guess once he's died, he won't be depressed anymore. The angle of elevation is measured upward from the horizontal. So this rabbit looking up at his certain doom, the vulture, would be looking up with an angle of elevation from the horizontal. Oh, I just spoiled my lovely color scheme of blue. Now, I want you to notice this angle of elevation can be measured anywhere on this horizontal line. So if I wanted to draw a triangle somewhere else, I could measure the same angle anywhere along this line. Also notice that the angle of depression and the angle of elevation are alternate interior angles. There's two horizontal lines cut by a transversal. These are alternate interior angles, therefore they are equal to each other. Lots of geometry and trigonometry if you haven't noticed. And the ant is there just to provide another angle of elevation up to the bunny if we so desire. But I don't know, maybe he's one of those soldier ants that cleans off the bones after the vulture has devoured the flesh, if you want to be disgusting about it. The next problem I want to look at is another application of this involving road grade. So sometimes you'll see in a mountainous area a road sign that looks like this saying that the grade of the road is 8%. Basically, grade is slope. It's measuring rise over run in a percentage form. So in other words, for every 100 feet the road that you travel in a horizontal direction, the road goes up 8 feet. So 8 over 100 is the 0.08. So what would be the angle of elevation of a road with a grade of 8 over 100? So here's my theta. That would be what I'd measure my angle of elevation up from the horizontal. So this would be my opposite side and my adjacent side of a right triangle. So I would say tangent of theta is equal to 8 over 100 or 0.08. And so theta is equal to inverse tangent of 0.08. Computing that on the calculator, we find that's about 4.57 degrees. So the angle of elevation is 4.57. Now, if we go down to another problem that uses a similar situation here, we have a mountain here, and we're building a tunnel through the mountain. On this side of the road, the ground is 800 feet above sea level. On this side, or I'm sorry, on this side of the mountain, the ground is at 900 feet above sea level. So basically, they're going to have to build a road down that goes down 100 feet to reach the same level on this side of the mountain, so that as they build the tunnel across, people tunneling from the right side and the left side will meet in the middle at a nice level road. So this is an engineering problem. I'm sure that has been done many times before. The engineers only want the road to have a grade of 5%. So down here we want the grade being 5%. So where do we have to start digging to get the road? So where do you start the road in order to have a grade of 5% and have it get down to the right level on the mountain? So first of all, let's examine the whole idea of the grade. And actually I've done some of the computations already, and they happen to be sitting right here, but I'm just going to talk through them. So here's my road. Right here is the road. And if I want it to have a 5% grade, that means for every 100 feet it goes horizontally, it goes 5 vertically. And so we're dealing with here the slope. And really it doesn't matter in the case of grade whether the slope is positive or negative. It's kind of just an absolute value of slope, if you want to think of it that way. So tangent here is tangent of theta is 5 over 100 or 0.05. So you can see over here I did inverse tangent of 0.05 and I got the angle of elevation to be 2.86. And actually I drew this triangle completely incorrectly. Let me try this again. What I'm looking for is the angle of elevation of the road, not the angle of depression. It turns out to be the same angle, but I'm really looking at this angle is what I'm thinking of the road, and this is being the 5 and this is the 100. Same angle. It turns out to be 2.86 degrees. So that's this little angle right here, 2.86 degrees. Now I want to know this distance here. How far from the mountain do they need to start digging their road down to make this road? So I'm looking for now a triangle that looks like this. And I know this distance is 100 because we already talked about the 900 feet above and the 800 feet above sea level. This distance is 100. We're trying to find that distance, and I need to know an angle. This will be a right angle. Well, I know from the same thing I just did a little earlier that alternate interior angles are the same. We've got two horizontal lines cut by a transversal. So this angle here is also 2.86. So this is 2.86. So once again, I have a tangent problem. I have tangent of 2.86 degrees is equal to a 100 over x. When you solve this for x, we end up with x is equal to 100 over tangent of 2.86 because I multiply both sides by x and then divide both sides by tangent. So I want you to notice something that on my calculator what I did here is once I know that this is 2.86, when I type it into my calculator, I type 100 and tangent, and then when my cursor is inside the parentheses, I up arrow to highlight this number and copy it, and then I push enter and it copies it into here. That way I get exactly the right answer. If I had just typed in 2.86241, I wouldn't have gotten exactly 2,000. And it turns out that this is the same slope of this line as this line. It's just two different triangles. So 5 over 100 is the same ratio as x over, or 100 over x. So 5 over 100 equals 100 over x. X ends up being 2,000. That's another way you could have done this problem, actually. Our last example is a problem we talked through in class. How do we find the angle of elevation of a school desk? So this is the desks that are hopefully a reasonable facsimile of the desks that are in the classroom. And so basically we're looking at what is the slanted part of the desk. And I have to create some sort of right triangle, but I don't know, but I have to use the measurements that I can take directly from the desk, not just sort of estimating. So if you measure the top of the desktop, you get this length right here, which is the slanted length of the top of the desk. If you measure from the front corner of the desk at the top, at the top edge of the desk, you get 74 down to the floor, and these are in centimeters. If you measure from the bottom edge, you get 71.5. The difference between the two measurements is how much the desk slants up. That's the 2.5. So down here you're measuring the 71.5. From here to here it would be the 74. The difference is 2.5. So that tells you the rise of this distance here. So now I have an opposite and a hypotenuse and an angle, so I'm going to use sine of theta is 2.5 over 47, use inverse sine of 2.5 over 47, and I get that the angle of elevation of the desk is about 3 degrees. When you just look at it, it looks steeper than that, but it's really not very steep. So this concludes the day 1 notes, and hopefully you should be able to do your first worksheet. There is a video to accompany the worksheet if you have some problems setting up any of the problems.